Compute-optimal scaling laws have long dictated frontier language model training. The famous Chinchilla rule demands 20 tokens per parameter. But visual generation. A new Luma AI study using the ABRA model family finally maps diffusion scaling laws, and the results fundamentally change how we should train them. Spanning 60 million to 2 billion parameters across 3 orders of magnitude of compute, the ABRA study reveals a stark difference. Diffusion models require roughly 200 image tokens per parameter to reach compute optimality. That is 10 times the data density of language models. This massive data hunger stems from higher dimensional image spaces, resolution-dependent information density, and inherently noisier training dynamics. Here's the critical practical takeaway. Diffusion training is remarkably robust to overtraining. While undertraining a large model catastrophically hurts performance, overtraining a smaller model with more data incurs a loss penalty of less than 0.5%. In compute-limited settings, always prioritize dataset size over parameter count. We also found that generation and representation scale heterogeneously. Linear probe accuracy for image understanding peaks at a much lower token count than generative quality. Furthermore, as models scale, the optimal classifier-free guidance scale naturally drifts downward. Stronger generative capacity actually requires less guidance. Finally, the study demonstrates scaling collapse for the first time in diffusion models. When trained compute-optimally, loss trajectories across different model sizes collapse onto a single universal curve, bounded only by seed noise. This gives us a powerful real-time diagnostic tool to verify training health. Even resolution shifts the optimal token count, pushing higher pixel densities toward more data-hungry regimes. The message is clear. Stop chasing model size. Scale your dataset, lean into overtraining, and use scaling collapse as your training compass. The future of visual generation is data-bound, not parameter-bound.